We now continue with the functions of bounded variation. So up to now we were looking at real valued functions. So now consider f, a vector valued map from AB to Rn. So f of x will be a n tuple f1 of x, fn of x. So each one fi is from AB to R, 1 less than equal to I less than equal to n. And then mod fx, this is a vector, so this is the usual Euclidean norm. So sigma I equals 1 to n mod fix square whole to the power of half. And we say that if you have P, any partition, we say TPF as usual equals sigma I equals 1 to n of mod f of xi minus f of xi minus 1, where mod of the vector is given by the Euclidean norm in this way. And therefore now you can say that TAB of f is as usual sup over all partitions of TPF. F is now a vector. Okay, so this is how, and f is BV, bounded variation, if TAB of f is less than plus infinity. Now given f, you can define integral AB f dm1. This is a vector now, so this is integral AB fi dm1 I equals 1 to n. So this is a n tuple. Similarly, f dashed at any x is the gradient. So you have f1 dashed x. It's not the gradient. This is fn dash x. This is derivative component wise. So this is the derivative of the fn capital N. Yeah. Okay. Fine. So now we have the usual estimation lemma, which is all important. So lemma, you have f AB to Rn integrable. Then integral AB f dm1, remember this is a vector and its modulus is the usual Euclidean norm, is less than equal to mod f, again Euclidean norm, dm1 over AB. So this is the usual theorem which you expect to have. So let's see how we prove this. So let us take y equals integral f AB dm1, therefore y equals y1 to yn and yi equals integral fi dm1 over AB, 1 less than equal to I less than equal to n. So now star trivially true if y is 0. So assume y is not 0. So what is mod y square? This is equal to sigma I equals 1 to n yi square, and then you don't need to put the modulus because it's a square of a real number, and that's equal to sigma I equals 1 to n. I am going to now write it as yi integral fi dm1. but that's equal to, since yi is now a number, I equals 1 to n integral of ab, sorry, sigma yi fi dm1. And now you apply the Cauchy-Schwarz inequality, mod of yi fi, so that's less than equal to integral ab mod y mod f dm1. Okay, so and that's equal to mod y is again a number, it comes out of the integral ab mod f dm1. So mod y is not 0, so divide both sides by mod y to get star. Proposition. So now we are going to imitate a proposition which we did earlier. So let f ab to Rn be continuously differentiable. That means its derivatives for each I, fi is continuously differentiable. Then f is bv and tab of f equals integral a to b mod f dm1. So proof. So f continuously differentiable, that means fi continuously differentiable for each I. So exactly as before. So you look up the previous proof, you get that tab of f is less than or equal to integral ab mod f dm1. So this is already done. For each you have to do it component wise, and then it's exactly like before. Now to prove the reverse inequality. Okay, so now what do? You take, so f dash continuous on AB implies uniformly continuous. Therefore, given any epsilon, there exists delta positive such that mod x minus y less than delta implies mod f dash x minus f dash y is less than epsilon. So P, any partition such that delta P, this is the maximum of all the subintervals, is less than delta, that is max 1 less than equal to I less than equal to n, xi minus 1 is less than delta. So if xi minus 1 less than equal to t less than equal to xi, then you have mod f dash t minus f dash xi is less than epsilon. So mod f dash t is less than equal to mod f dash of xi plus epsilon. So that implies that integral xi minus 1 to xi of mod f dash t dt minus epsilon xi minus 1 is less than or equal to mod f dash xi. So I am just integrated, I brought the epsilon to this side and integrated it, and therefore I get mod f dash xi into xi minus 1. And that is written as modulus integral xi minus 1 to xi of, I am going to add and subtract f dash t plus f dash xi minus f dash t. dt, because these two get cancelled, first and the third term gets cancelled, the middle one is a constant, so you will just get f dash xi xi minus 1. Complete the modulus. Now we can break this is less than or equal to integral xi minus 1 to xi mod f dash t, sorry, I'll put the modulus here, I will still not use it, plus integral xi minus 1 xi f dash xi minus f dash t dt. But f is continuously differentiable, and this integral here xi minus 1 to xi f dash t deta is nothing but mod f of xi minus f of xi minus 1 plus, here if you take the modulus inside in the second integral, that is less than epsilon in this interval, we know, and therefore that is less than epsilon times xi minus 1. So now you sum over all I, so you get integral a to b mod f dash t dt is less than or equal to, so if you sum over all these things, that will give you TPF plus, you will just get epsilon times b minus a, and here also you have minus epsilon times b minus a in the first, because of the summation of this term. Okay. In other words, integral a to b mod f dash t dt is less than or equal to TAB of f plus 2 epsilon times b minus a, and of course this is nothing but integral a to b mod f dash dm1, because it's continuously differentiable, continuous map, and therefore it's Riemann integrable, etc, etc, etc. And therefore this is now you can let epsilon go to 0, because epsilon is arbitrarily chosen, and so you get integral ab mod f dash dm1 is equal to TAB of f, less than or equal to TAB of f, and you have the other reverse inequality also, and therefore you have the equality. Okay, so this proves the theorem. So now let us consider, so example, rectifiable arcs. So an arc or a curve in the plane is a continuous map gamma from say 0 AB into R2. So how do you compute the length of what do we mean by the length of the curve? So what we do is take P, partition of AB, and then you take sigma I equals 1 to n mod gamma Ti minus gamma xi, if you like, gamma xi minus 1. This will be equal to sum of the lengths of the chord joining gamma xi minus 1 and gamma xi 1 less than equal to I less than equal to n. So you have a curve like this for each. So you have gamma x1, gamma x2, gamma x3, you mark off the points and then you join these by straight lines and then sum of the length. And we say arc is rectifiable, that is length is well defined if sup over all partitions of sigma gamma I this is finite. In other words, that is, arc is rectifiable if and only if gamma is BV and length is precisely TAB of gamma. So length of a curve is nothing but the total variation of the curve, and the function has to be a bounded variation. So now let us assume gamma is given parametrically as gamma t equals xt yt and x y continuously differentiable. Then by above proposition TAB of gamma equals integral mod gamma dash dt, which is equal to integral a to b square root of x dot t square plus y dot t square, and this is exactly the formula which we have studied in the original calculus courses for the length of a curve which is differentiable. Okay, so this is we recovered that formula in this case. We have proved something more general. Now we come back to real valued functions. So proposition f ab to r integrable. Then the indefinite integral of f defined by capital F of x equals integral a to x f dm1 for x in AB is a uniformly continuous function of bounded variation. Proof. So fx minus fy modulus is nothing but mod integral xy, whichever is bigger, okay, assume mod f dm1. Which is less than or equal to integral xy mod f dm1. Now f is integrable, that is, given epsilon positive, there exists a delta positive such that mod x minus y less than delta, that is the measure of this interval less than delta, implies integral over xy mod f dm1 is less than epsilon. So this is the what we call the absolute continuity of the indefinite integral. We have proved this already for the integrable functions, and therefore we have, so this implies that capital F is uniformly continuous. Now let P A equals x naught less than x1, xn equal to b, be a partition of AB. Then you have sigma mod f of xi minus f of xi minus 1, I equals 1 to n, is less than or equal to sigma I equals 1 to n integral xi minus 1 xi of mod f dm1 by definition, and that's equal to integral ab mod f dm1, and that is of course finite. Therefore we have TPF, therefore TAB of capital F, which is the supremum of all such things, is less than integral mod f dm1 over AB, and that is finite. So capital F is of bounded variation. So if you want, for instance, we were asking the question, when can you write a function f of x equal to or f of x minus f of a equals integral f dash t dt. When f is differentiable, and we said for instance the Cantor function you cannot do it, and the reason is because if you have an indefinite integral which a to x, sorry, this is the indefinite integral, even if f dash is integrable, then the original function is uniformly continuous and of bounded variation. So that already places a set of restriction on functions for which the theorem can be true. Therefore, if you have a function which is differentiable almost everywhere, then if you have a hope for the fundamental theorem of calculus to be true, it has to be uniformly continuous and of bounded variation. In the next section, little later, we will give you a complete set of necessary and sufficient conditions which will tell you when you can actually do this. Even this is not enough, but this is at least a necessary condition. So we will continue a study of the indefinite integral in the next session. Okay.